Okay, so we've already seen that just by thinking about category theory and thinking about questions like what kind of arrows are in monomorphisms, we can gain quite a lot of understanding about ideas to do with limits. For example, products and equalizers. And we've just seen that using some of these more kind of specialized notions from topos theory, involving things like the Mitchell-Benebow language and so on, we can understand quite a lot about some more sophisticated kind of concepts like the nature of monomorphisms, epimorphisms, classifying arrows, and so on. And we're going to see shortly that these sort of Mitchell-Benebow language ideas can also be applied to understand things about co-products, co-equalizers, initial objects, and so on, basically the co-limits. However, there's something else which is very important to realise, and this is the idea of arrows. Okay? I mean, of course, category theory is largely about arrows, and there's this important question of what kind of arrows are there from one object to another object? What is the nature of them? How can they be represented? And so on. And so there's an important notion which sort of links a lot of this kind of language and ideas with the study of, what arrows there are. And this is the idea of what's called a functional relation. Okay, so suppose we have a couple of objects, A and B, now in a topos. Okay, now a relation would be a subobject of A times B. So, for example, a monomorphism R from an object capital R into A times B. That would be a relation. And there's a certain kind of relation called a functional relation, which basically describes an arrow from A to B. And so we're going to understand quite a lot about this with different results, but the sort of short story is basically that one of these relations looks like a graph. Okay, so if you remember, there is this idea of what we might call the graph. So let's suppose we have an arrow f from A to B. Well, then the graph of f is this arrow, which we could write as identity A, comma f. So we can think of it as a arrow from A to A times B. Now, it's also true that such a thing is a monomorphism, so we can see that quite easily, because if we do this after x and we get the same result as doing it after y, well, then we have 1a. Well, then we have x, comma fx equals y, comma fy, and therefore we have x equals y because the first components of these are equal. So x must equal y. And therefore, this arrow has a property that if doing it after x gives the same result as doing it after y, then x has to equal y. Therefore, this is a monomorphism. But if you think about it, this is really much more. It's actually, well, okay, maybe it's not immediately obvious, but it is in fact the case that this really has all the information of this kind of arrow f. Okay, so this is pretty clear, like a very clear example is when you are thinking about the case of the category of sets. If you think about A and B being sets of real numbers. Okay, so think about a graph of a function, like this, for example. So here we have A, and here we have B. Now we have this subset of A times B, written like this. So from any given point on A, we're sort of sending that to, so say a point X along the line A. Say this is A, here's point X. Well, that's going to get sent under this arrow here. This arrow, which is the graph of F. This point is, of course, going to get sent to the point X, Fx. Okay, and that's going to be some point on here. So you can see that basically the information about this function f is being encoded in this graph. It's actually a very interesting kind of idea that, you know, you can encode this idea of an arrow as a kind of sub-object. But what's much more remarkable is that this kind of thing is possible not just, but what's much more remarkable is that this kind of idea is possible not just for this case of like a function from reals to reals, but it's possible for any function in the category of sets. In fact, it's possible for any arrow in any topos. Okay, so we're going to start to understand this idea. But to get there, this is an important kind of result that we want to get our head around. This theorem 16.5 from McClarty. And what it says is that suppose we have a relation R, so a sub-object R of A times B. And then the question that this theorem deals with is, when does this sub-object R look like the graph of some arrow? Okay, now naively, like suppose R was the graph of some arrow. So suppose R was identity A, comma F. Well, in that case, this sort of first component here, H, would be identity A, which is a kind of isomorphism. But if you think about it, that's just a case where, you know, it just happens that this is actually an identity arrow. But what's the difference between an isomorphism and an identity arrow? Well, if you're really thinking in sorts of categorical terms, in some sense, there's not much difference. Okay, if you don't really care how elements are labeled, it's difficult to distinguish between a kind of isomorphism and a identity arrow. So there ought to be a case then where R looks like a graph, even though its first component, when we write R as this two-component thing, when we write R equals H comma K, which we should because it's an arrow into A times B. Well, when we write it like that, there could be a case where R basically looks like a graph of some arrow, but where H is not an identity arrow. Maybe H is just an isomorphism, okay? And in that case, what will this... So in that case, let's say we have a R is equivalent to some graph, but it's not equal to some graph, because H is an isomorphism, but it's not necessarily an identity arrow. Well, in that case, which graph is it going to be isomorphic to? Well, think about the case of the category of sets. So we'd be forming some graph, like in this case where H is an isomorphism, we'd be forming some graph by, for our first component, we would be doing H comma K after the inverse of H. So that would be kind of like this. And that would be H comma K after the inverse of H, which would give us identity A comma K to the H minus 1, K after H to the minus 1. And so that would be the graph which our kind of relation R would be equivalent to in this kind of case. So this is the basic idea. So this is the sort of idea behind the result, basically, is when we can consider this relation R to be equivalent to some graph. Okay, so let me just go through the result now, because there are some technicalities. So here we go. Suppose we have a relation R, which is a subobject of A times B, and we can write it as H comma K. Now, the idea is that we're going to have that H is an isomorphism. Okay, so this first component of this arrow R is going to be an isomorphism if and only if there exists some arrow F from A to B, which is such that H comma K, or if we like R, is equivalent to the graph of F, where F is K after H inverse. Okay, so this is kind of similar to what I was just talking about, but let's just go through the proof now, because it's easier if we see all the kind of technicalities. So we want to prove this result. So firstly, let's indeed suppose that R here, which R is equal to H comma K, let's suppose that that is indeed equivalent to some graph. So we'll assume that H comma K is equivalent to identity A comma F. Okay then, so what does that mean? Well, here is R, and here's our graph, and we're supposing that these two things are equivalent. So what does that mean? Well, it means that we have that R is contained in the graph, and also that the graph is contained in R. So from the fact that R is contained in the graph, we have that R is equal to the graph after I. So when I say the graph of F, that's kind of an abbreviation for basically saying that we have identity A after F paired. Okay, that's what I mean by the graph of F. So to say that R is in the graph of F, we mean that R is equal to identity A comma F after I. So that's this kind of situation. And also to say that the graph of F is in R, we have that identity A comma F is equal to R after J, where J is some arrow going the other way. And to say that R is equivalent to the graph of F is basically to say that R is contained in the graph of F, and the graph of F is contained in R. Okay, so basically we have these two equations here. Now we can infer some stuff from these. So let's take this second one. The graph of f is equal to r after j. Well, then we can use this up here to rewrite this as the graph of as being equal to the graph of f after I after j. And we could also write this graph of f as the graph of f after identity of r. And the fact that the graph of f is a monomorphism then gives us that I after j is equal to the identity arrow of a. And then we can do a very similar kind of trick to get that j after I is equal to the identity arrow of r, using this kind of argument, again exploiting the idea that r is a monomorphism. Okay, so basically between these two kind of equations here, we have that I is going to be an isomorphism and j is going to be the inverse of it. Okay, so we have this kind of situation, and we basically have that r is going to be equivalent to this graph of f. Well, okay, we're really just fleshing out like some of the kind of isomorphisms which occur because of sub-objects being equivalent, actually. But anyway, we now have that this arrow I from R to A is an isomorphism. But here's the thing. If we look at this diagram, we're supposing that the graph of f after I is equal to R. And we know that R is something we can write as h comma k. So let's take this equation and then we're going to do P1 after it. So this gives us that P1 after the graph of f after I is equal to P1 after h comma k. So basically we end up getting, from this right hand side we get h, and from this left hand side we get an I, so we get I equals h. And we know that I is an isomorphism, so that means h is an isomorphism. Also, okay, so look, let's just have another look at our result. So we assumed that h comma k was equivalent to our graph, and we got h as when we got that h is an isomorphism. We also want to get that f is equal to k after h to the minus 1. We'll get that now. So we can write f as p2 after the graph of f. And we know we can write the graph of f as r after j. We did that up here. So we write f is equal to p2 after r after j. Or we could write that as p2 after r after I to the minus 1. And we know that I equals h, so we can write that as p2 after r after h to the minus 1. And we know that r is h comma k, so we can rewrite this as p2 after h comma k after h to the minus 1, which is equal to k after h to the minus 1. So we've understood the nature of f to be what we thought it was, as I comment here. Okay. So basically we've proved it this way. Now let's go the other way around. So conversely, let's now suppose that h is an isomorphism. And what we're going to do is we're going to let f equal k after h to the minus 1. And we're allowed to write h to the minus 1 because we know h is an isomorphism now. And now here's the thing. We have this arrow h from r to a, and we also have this arrow h to the minus 1 from a to r. And now the thing is that we do indeed have that h comma k, which is r, okay, h comma k is always r. We have that h comma k is in identity a, comma k after h to the minus 1. And this thing here on the right, this is actually just the graph of f, the way we're thinking of f. But this is a bit more explicit to write it like this. But anyway, the thing is that we do indeed have that h comma k is in this graph of f here. Why? Well, because consider identity a, comma k h to the minus 1 after h. Okay, so that's going to be this kind of composition like this. Well, the h just goes inside and we end up with a h comma k. H comma k, alright? So basically that shows that we have this kind of equation holding, and that therefore shows that h comma k is in the graph of f. Now the other way around, we also have the graph of f, which I'm writing as identity a, comma k after h to the minus 1 to be a bit more explicit. But anyway, we have that the graph of f is in h comma k. Why is that? Well, just consider what we get if we do h comma k after h to the minus 1. That's this kind of composition here. Well, then we get identity a, comma k after h to the minus 1, which is indeed just this graph of f here. So yes, basically what we have is that h comma k is contained in the graph of f, and the graph of f is contained in h comma k, and so what we basically have is that these two sub-objects here are equivalent to each other. And therefore we have that r is equivalent to the graph of f, where f is k after h to the minus 1, which is indeed just what we wanted to prove. So we're done. We've shown that in the case where h is an isomorphism, we have that r is equivalent to the graph of f, where f is k after h to the minus 1.